Now that we've gone after, or talked about, we haven't really gone after, now that we've talked about pathogens, what can make you sick, we're going to talk about how your body deals with it. I use the term pathogen, and that's an organism that's going to make you sick. I also will use the word antigen. Remember, antigens are proteins on cell membranes. And so with these pathogens, they have antigens, and your body's going to see those antigens as being foreign. And that's how it's going to identify that you've been attacked by something foreign, and then it's going to induce an attack against that pathogen or antigen. So your nonspecific or innate response, this is like it says, it's nonspecific. It's like our first line of defense against something that can make you sick or that it sees as being foreign. So it doesn't really care what it is that's foreign. It doesn't care what it is, it just knows that it's foreign, and it's going to induce the same response to anything that's foreign. So the advantage of this is that it allows your body to go after something very quickly. The disadvantage is that it's not a very specific attack to that pathogen. So it will get us started, but you'll see later how the body's going to use other methods to induce an attack that is very specific. So in this example, the body reacts the same way no matter what the invader is. The ability to destroy an invader does not improve each time that it's exposed to that pathogen or antigen. This will make more sense when you do specific immunity. And again, you get the same response for any invader. It sees something foreign, it goes after it. Now, there are several different types and examples of nonspecific immunity. I'm just going to talk about these three. So the first one is inflammation. So imagine you get a cut, and you don't take care of it. And so it starts to get red, you start to get pus in it. What that is that's an inflammatory response, and your body responding to the pathogens that have entered through your skin. So what happens is white blood cells will be attracted to that area. Blood will be attracted to that area that has the white blood cells. That's why it turns red. That's why it gets warm. And they will start attacking any pathogens or foreign antigens that are in that area. One of the examples of the type of cells that will do that are natural killer cells. And you can think of them as being like Pac-Man. So they're going to come after, they're going to see little bacteria, and they're going to waka them. And fill up with them and try to get rid of them. So what pus is when these white blood cells get filled with these pathogens, they just have to die. And so pus is actually a bunch of dead white blood cells. So what it is it's showing you, it's good and bad. It's telling you, yes, there's an infection there, but what it's also telling is that you have an infection, but that it is responding to it. But obviously, if you get pus and stuff, you know that you have to do more than you are doing. The third one is a fever. So what a fever is if you get an infection, it doesn't have to be a cut, because most of the time when you think about it, when you have a fever, you don't have a cut like that. But you've been attacked by some type of pathogen. Your white blood cells are doing what they need to do within the body, and they start sending out these signals called pyrogens. And what these pyrogens do is they travel through the bloodstream, and they actually cause the hypothalamus to raise your set point. So your set point, 98.6, what it does, it raises your set point up. So let's say 100.5. So now your body has to go from 98.6 to 100.5. It raises your body temperature, and that's what a fever is. And what a fever does is it actually puts your body in a better frame of mind, to put it in simple terms, to fight off the infection. Or by raising the temperature, bacteria and viruses don't do as well. It also stimulates your white blood cells to do more, to try to attack the pathogen. So fevers are not necessarily bad. They tell you, yes, that you have an infection, but they are actually helping your body to fight that infection. So if you have a low-grade fever for a short amount of time, just let it go. Okay, let it go. Now, if you have a low fever and it goes on for an extended period of time, then yes, you need to get it checked out. If the fever starts going above like 102.5 and stuff, you need to try to bring it down somewhat. And then again, if it goes too high, 103, 104, you obviously need to get some help. But again, the goal of a fever is actually to help your immune system to do its job. Okay, so what are allergies? Allergies are an inflammatory response, an improper inflammatory response. So your body's exposed to what it defines as being a foreign antigen. So cat dander, peanut dust. For some reason, your body sees that as being foreign and goes after it just like it would go after something that really is bad for you. And so what your body's trying to do is trying to fight it off. So it releases these histamines that make your capillaries leaky. And what that does, it causes you to get a runny nose, your nose gets red, you're coughing, all of these things, your eyes water, all of these things are being designed to get rid of that antigen, okay, to get rid of that antigen. Now, most allergies are focused in the upper respiratory system, okay, and in your head. They're not full body allergies, okay? They're not full body allergies. So these release of histamines make the capillaries leaky, which leads to the symptoms of allergies. So a lot of or allergy medications you take are antihistamines. They work against the histamine, which then stops the symptoms. Now, some people have an anaphylaxis type of allergy. This is a full body allergy. So if cat dander, but peanut dust or peanuts in there, if they get a small amount of peanuts in their system through their, mouth or through their nose, what happens is it's not just their upper respiratory and head that responds, it's their whole body. So what occurs is that all the capillaries become leaky. A full body capillaries become leaky and their blood pressure will plummet. And so that is not good. You need your blood pressure to do what it needs to do, to get blood where it needs to go. So when you hear about anaphylactic shock, that's what that is. And so when they have EpiPens, an EpiPen, if someone's having a full anaphylactic, goes into anaphylactic shock, you give them the EpiPen. It mimics the sympathetic nervous system, which raises your blood pressure. And so that's why people have to have EpiPens that have severe allergies. Another example is bee stings. For most people, a bee sting causes a local inflammatory response. In people with severe allergies, that bee sting causes a full body allergic response. Okay, just a little trivia here. It's interesting when we look at what the average temperature is of a person. We always use 98.6, which is what I used. But when you look at when that was developed, that was in 1868. That is a long time ago. So how and what kind of thermometers they were using, I don't know. So in 1992, there was another study done and it was slightly lower. And actually an article has come out recently, and I'm doing this in spring of 2020, that showed that the average temperature is actually going down overall. So they're not sure why that happens. So they're now showing numbers in the 97.5s or 97.6s. Okay, so you hear about, you should have chicken soup, blah, blah, blah. So here's our ethical dilemma for the day. Chicken soup has been shown to help. There are chemicals in it that can make you feel better. But the problem is if you're a chicken. And so if you're a chicken and you have the flu, do you eat the chicken soup? Is it maybe yes if it's not your relative, maybe no if it is a relative. That's just something you will have to decide if you ever come back as a chicken. Okay, so now we're going to start the discussion on the adaptive or specific response. So this adaptive immune system elicits an attack against a particular invader, against a particular antigen. So this is going to take longer because your body has to develop an army that's going to attack that specific invader. The attack against each individual invader is different. So how you attack one bacteria is going to be different than how you attack another bacteria. So again, it takes time for your body to develop that attack against a specific invader. The nice thing about our adaptive system is that it will remember how it attacked that invader. So if you're ever attacked by that invader again, it will go after it immediately. So you won't have the delay that you're going to normally see with the specific response. So in my generation, we did not have the chickenpox vaccine. So we got the chickenpox. So if you get the chickenpox, or got the chickenpox, then you would not get them again, because when your body goes through this whole attack mode, then what happens is it remembers that. It keeps a little bit of that army there. So if you're ever introduced to the chickenpox virus again, then it will go after it immediately. So this one has memory. It has memory. Okay, so adaptive immunity, it's antigen specific, so a very specific pathogen, a very specific antigen. It is systemic. It's going to run throughout your whole body. And like I just told you, it has memory. It's going to remember that it induced this attack. And if you're attacked again in 5-10 years, it's ready to go. The attack is ready to go very quickly. Okay, so we have two ways, and there's going to be a video on each of these. Adaptive immunity involves two methods of cell-mediated and antibody-mediated immunity. These two systems involve two basic types of lymphocytes, B cells and T cells. Remember, leukocytes are white blood cells. Lymphocytes are a type of leukocyte. So leukocyte, term for white blood cells. These lymphocytes are a specific type of white blood cell. T cells mature in the thymus. The thymus is a gland that sits right above your heart. When you were young, it was pretty significant because your immune system was maturing during this time. Right now, if you're above 13, which most of you probably are, it kind of shrivels away as you get older into your teen years because it's done. It's made all the T cells, types of T cells it's going to make, and it kind of shrivels away. So it's not your thyroid gland, it's your thymus gland, which is below, closer to the heart. And B cells mature in the bone marrow. Okay, so I'm going to go through how your body's going to identify that it's been attacked, and that will help you as you go through the next two videos. Okay, so here's a regular body cell, and here are your specific, your self antigens, the antigens that are normally on your cells of your body, the antigens on your body that say, this is me, okay, this is me. And so when your immune system goes around, it's looking for those antigens. If it sees these antigens, then it knows it's you, it's going to leave it alone. But let's say a body cell gets attacked by a virus, and we've talked about how viruses need to exist within a body cell. What's going to happen is, remember, the virus has to be inside the cell. So how's your immune system going to know whether it's been attacked by a virus or not? What's going to happen is your cell, in its last-ditch effort to save the body, is going to take a piece of that virus and place it on your protein. Now what happens is, over here, if a white blood cell comes by, it says, okay, all these proteins are us, I'm going to leave it alone. But then if it comes over here, it's going to say, hey, there's a different shape here. This cell has been attacked, and that's going to cause it then to do it's going to start the process of developing an immune attack against that virus. So again, this changes the shape, which allows the white blood cells to then know that something is happening and we need to induce an attack. So how do B cells and T cells identify self versus non-self? Okay, you've heard of antibodies. The technical word for antibodies is immunoglobulins. Okay, they are Y-shaped. We did these when we did blood typing. So go back and think about, you had these Y-shaped structures. Okay, the constant region, don't worry about the variable region. Remember at the end of the Y's, they had different shapes, okay? They had different shapes. So you've got these Y structures with these different shapes, and every shape is going to be, there are going to be several thousands of different shaped antibodies. And so what happens is, if the end of that antibody, the end of the Y, that shape fits the antigen, then it's going to induce an immune response. Okay, it's going to induce an immune response. So your body has to find the antibody that fits into the antigen that is causing you to be sick, the foreign antigen. So an antibody can be free floating. Here's your little Y's. They can float around your bloodstream. They can also be attached to a B cell. So these antibodies can go after something foreign. These B cells with the antibodies attached to them can also go after the same antigen and attack it. T cell receptors are just like antibodies, but they're not. They're similar to antibodies, but they have the same idea. They have this region that looks like a Y, and then at the end of that Y, they have regions of different shapes. And so the difference here is that these T cell receptors are attached to T cells. So that's why we call them T cell receptors, not antibodies. They are on T cells, not B cells, and they are not free floating. They can't float around. Okay, so this is going to be an introduction to the specific immunity. You have cell-mediated, which is going to go after viruses, and you're going to have antibody-mediated, which is going to go after bacteria. So antibody-mediated, you're going to be dealing primarily with B cells, specifically plasma B and memory B cells. And then in cell-mediated, which goes after viruses, you're going to have the different T cells, memory T cells, cytotoxic T cells, and helper T cells. And I want you to notice this little arrow here. Helper T cells are also going to be important for antibody-mediated immunity. So this is the end of this video, and then you will see there's a video on cell-mediated and antibody-mediated immunity. You need to watch those, take notes on those, and make sure that you understand the processes in which they work or the way that they work. All right, that's it for this video.